This will be our second video on the arithmetic series. We are going to define a couple different things and have a new formula. So arithmetic series and sums. The sum of an arithmetic series is infinite, so we say that the sum does not exist. Because if we tried to add up an infinite number of numbers, they would get infinitely big. And so since it doesn't ever become a single number, and a series is a single number, we say it doesn't exist, or it's undefined. However, the sum of only part of the series does exist. This is called the nth partial sum. This is the sum from the first term, not necessarily the number 1. It's the sum from the first term to the nth term of that series. So this is called the nth partial sum. And we have a formula, Sn, so the sum of the first n terms. Sometimes we write n as a subscript. Sn is equal to n times a1 times an. So the first term and the last term, which is our nth term, all divided by 2, where n is the number of terms from the sequence being added together. So I am going to copy this so I can paste it onto the next slide, where we are going to do a couple examples. So we'll have this up in the corner. We need to identify n, a1, and an. These are the 3 numbers that tell us the value of the partial sum. So we're given an expression. So n, don't be confused. The n, that's the index, is different from the n. This is always going to be the value at top. So n is 50. So a1, our first term, is going to be 3 times 1, so just 3. An is going to be 3 times 50, or 150. And so our formula says it's S50 is going to be 50 times 3 plus 150, all divided by 2. Now you can evaluate these by hand. You can also evaluate it by calculator. So I'm going to plug this into my calculator. Let's see, I have 50 times, in parentheses, 3 plus 150, all divided by 2. And that gives me 3,825. Now let's try a different one. I guess I can change to a color that I haven't used at all this lesson. So again, we need to identify n, a1, and an. So n is going to be the top number. So 135. N is the upper bound, or that limit that we had discussed in the last video. The first term is going to be 2n. So 2 times 1 minus 5, so we get -3. And if I plug this into my calculator, I have 2 times 135 minus 5. And so 2 times 135 minus 5 is 265. So 265. So our formula says that S of 135, notice that you can use the subscript or the parentheses, is going to equal n, so 135 times -3 plus 265, all divided by 2. And so once more, I'm going to put this into my calculator. 135, parentheses, -3 plus 265, close parentheses, and then divide that all by 2. And that gives me the number, it's a large one, 17,685. So the beauty of this formula is we wouldn't want to make a table of 50 terms or 135 terms. And yet, in about the same amount of time as we did the previous examples in the last video, we were able to calculate these very large sums using this formula. So let's do a couple more examples. This one, even though we could realistically make a table with 17 columns, it's not going to be the most fun. So let's not. So we need to know n, a1, and an. So n is 17, that's the upper bound. A1 is if we plug in 1 for I, we get 7 minus 5, which gives us 2. And now we have to plug in 17. So that would be 7 minus 5 times 17. I'm also going to put that into my calculator. So 7 minus 5 times 17 gives me negative 78. So our formula says our 17th partial sum is going to be equal to n, so 17, times our first term plus our second term. Since this is negative, I can just put a minus sign there, all divided by 2. Notice that the subscript always matches that first number in the numerator. So once more, putting this into my calculator, I have 17, then in parentheses, 2 minus 78, all divided by 2. And this gives us the sum of negative 646. So this is a powerful tool because it even helps us when we get negative answers as our sums. Our last example is going to be the 8th partial sum for the series. Now, we could use the formula, or we could write out the 8th number, but I want to use the formula. So we need to know n, a1, and an. So we know that n is 8. We know that our first term is 3. We don't know our 8th term. So what I'm going to do is, because I can find the common difference, I'm going to write an expression for an. So to go from 3 to 8, we add 5. To go from 8 to 13, we add 5. So our common difference is 5. So just as in our last lesson, we're going to have our first term, 3, plus our common difference times n minus 1. But remember, n is 8. So we have 3 plus 5 times 7. 5 times 7 is 35, if I'm not mistaken. I don't know why I'm drawing a plus sign. Oh, it all went away. Okay. I'll just erase that and go back. I suppose I should check that 5 times 7 is in fact 35. Yes, it is. So 3 plus 35 is 38. And now I have everything we need for the formula. So giving ourselves just a little bit more space. Our 8th partial sum is going to be equal to 8 times 3 plus 38, all divided by 2. Once more, putting this into my calculator, 8 parentheses 3 plus 38, all divided by 2. 164. There we go. So I might do a bonus video to prove where this formula comes from, but I hope that now that you've seen a few examples, you feel confident in using this formula to evaluate the sums of arithmetic series.